We had to protect them over about 4 years while we were building from scratch to completion. All the time, kept them running, never created inconvenience for the passengers.
Once excavation was complete, there was the burden of moving the excavated landfill. To remove the 1,000,000 cubic yards or 100,000 truckloads worth of landfill, the solution by Austin Tobin seemed to be a win-win situation.
Instead of carting this dirt all the way to New Jersey or hauling it way out to sea, simply place it on the west side of West Street. But not just to dump it in the river, but to carefully contain it within a series of cofferdams, such as, in effect, you would be increasing the size of New York City. And that's precisely what they did. They measured out an area just west of West Street, which would extend 700 feet out into the Hudson River, be 1,400 feet long, in other words, about the size of 6 city blocks.
They built a drum-shaped box of cellular cofferdams, a watertight enclosure to hold the material excavated from the building site.
These were really like big sunken cylinders, each 63 feet in diameter, each one filled with 6,000 cubic yards of sand. So you would create this barrier 700 feet out to the river and 1,400 feet long, behind which you would put the excavated fill and thus create 23 acres of new land.
As a result of the excavated material, the landfill created some of the most valuable real estate in the country. New York got $90 million worth of land that would eventually become Battery Park and the World Financial Center. Although the foundations were in place, there was still the problem of bringing thousands of tons of steel up over 100 floors. In past construction of skyscrapers, derricks were used. But a derrick had to be constantly lifted to a higher position, one floor at a time, costing several man-hours. Derricks also had to be powered from the ground, with extremely long cables running down through the floor already built. The answer was a self-powered crane that came from across the globe.
These were the so-called kangaroo cranes, nicknamed because they're coming from Australia, and they were put at the corner of each building. And what these kangaroo cranes essentially were able to do was to hoist themselves up with automatic machinery built into the crane, such that the crane could rise as the building went up.
The crane's diesel motors supplied the power, driving a series of hydraulic lifts installed at the base of each corner.
Then an interesting problem at the very end is how do you get the kangaroo crane down? And the way that was done is they had to be disassembled and brought down by elevator.
The cranes would raise a structure unlike any in the world. Before the buildings would be finished, more radical construction and engineering methods would forever change how skyscrapers were built. Construction of the Twin Towers began in August 1968. Architect Minoru Yamasaki would move away from conventional techniques with a completely different type of skeleton.
The common sense way of understanding the construction of a skyscraper, we think back to our childhood, is building it like an erector set. You have little pieces of steel which you hold together with rivets and grommets, and it's like building a cage. This is the normal way of building a steel skyscraper. It's a cage-like construction. You have vertical members and horizontal members, and you build little boxes, and you pile box upon box upon box, and thus you have a skyscraper. Yamasaki wanted something different.
What he decided on was a revolutionary way of constructing high-rises, the exterior skeleton system.
What Yamasaki came up with, in conjunction with structural engineers, is to make the skin of the building much stronger so that you wouldn't need internal columns.
Ever since the 19th century, skyscrapers have been built with a network of interior supporting columns. Their exterior walls were merely curtain walls that admitted light and kept out the rain. But in the World Trade Center, its tough exterior walls would carry the vertical loads and have the strength to resist the enormous force of lateral winds as well. High-strength steel that had not been available before made this possible.